Hello class. So welcome to the last topic in this week's material, week 3. So in the previous recordings we studied chapter 14 material, advanced MOS topics. We looked at some past transistor logic circuits, dynamic MOS, and we also briefly studied pseudo NMOS logic. So this recording and the next one, together we address a very basic topic in memory circuits called latches and flip-flops. So we don't really study too much of memory. Now chapter 15 in the textbook is devoted entirely to memory circuits, but the most basic concept that you need to know to understand more advanced memory ideas is this latches and flip-flops. So we'll spend some time in this course, in today in this recording, to look at latches and flip-flops. So beyond this, if you're more interested in memory and other forms of circuits that support memory, you have to wait till you move on to your next year of study and take some more advanced courses. But as far as this course goes, this is the one and only topic related to memory that we'll study. Okay, so having said that, let's move on. I'm on slide 39. I'll expand this. So in this recording, I will look at the theory about these latches and flip-flops. In the next recording, of course, we'll do some problems. So with that, we finish week 3 material. Okay. So while I'm not spending too much time on memory, I did want to walk you through some basic ideas. This is all from our textbook. Again, I advise you to read chapter 15 a couple of times, at least the first part, so that you understand, you get more details from the textbook than I can just give you in a lecture. So the logic circuits we have studied so far are called combinational circuits. Their output depends only on the present value of the inputs. Thus, these circuits do not have memory. So you must remember the difference between combinational circuits and sequential circuits when it comes to, logic circuits. Sequential circuits are circuits that incorporate memory. Their output depends not only on the present value of the input, but also on the input's previous values. And that's why we say the circuit kind of remembers what happened in the past. And that remembering property is memory, really, right? So such circuits are called sequential circuits. Also importantly, such circuits require a timing generator or a clock for their operation. So there are basically two approaches for providing memory to a digital circuit. Now I know that you probably by this time have studied enough digital logic and microprocessor design, etc., and even computer architecture, that you understand memory, different types of memory, how uh, the processor in a computer interacts with the memory and other I/O devices. So obviously none of this is really new to you, but the one thing I'll tell you is the reason why we are studying this here is because while it's one thing to say I can go get some data from memory, to be able to understand how the hardware or the transistors or the inverters actually implement the process of storing and retrieving information, and what are the conditions within the transistors and the ICs that you have to meet from a circuit's perspective to make memory happen. So that's the focus of this particular lecture on memory. So I'm sure you know memory by now, you know how to use it and all that, but here we do a little more of the underlying physics and circuits behind memory. So there are two approaches for providing memory to a digital circuit. The first is static sequential. Remember, all memory circuits are sequential circuits. A static sequential is a bistable circuit that can be used to store one bit of information. A bistable circuit means it has two stable conditions. In one stable condition or one stable state, it is said that a 0 is being stored. In another stable state, you say a 1 is being stored. And we know all digital logic just is based on zeros and ones. Hundreds of megabytes of information of practical use is stored in the form of zeros and ones. You know that. So a circuit that can store either a 0 or a 1 is a bistable sequential circuit. And again, bistable meaning two states, two stable states, and one stable state has a 0 in it and the other stable state may have a 1 in it. So dynamic sequential, that's the other type of memory. So there's a static sequential, there's a dynamic sequential. The other approach to realizing memory utilizes the storage of charge on a capacitor. So we know that when a capacitor is charged, it has a certain voltage, and if it is charged to a certain value or above a certain value, we can say, okay, that represents a 1, a high. And if there is no charge or its charge falls below a certain low limit, then we can say it's a 0. So that's another way to store zeros and ones into a circuit and call it a memory circuit. So static sequential and dynamic sequential are the two methods. Static sequential, the advantage of static is once you put something into the circuit and it stores it either as a 0 or 1, you can forget about it. It doesn't need any further power or charge to hold it. Dynamic sequential, on the other hand, is putting charge into a capacitor. And we know capacitors have a tendency to leak. They can lose charge. So in a dynamic sequential system, you have to keep refreshing. That means you have to keep adding the same charge to the capacitor if you want the high value to continue to be retained. So every so often, maybe once every clock cycle or once every 5 clock cycles, you have to put one more burst of charge into the capacitor, and that recharging process is why we call it a dynamic process. All right, so with that very basic introduction to memory, let's move on to the one topic that we want to study here in this recording in some detail, and that is section 15.1 in our textbook. So 15.1 has 5 topics again under it. 15.1.1 is the latch. From the latch, we go to the SR flip-flop, set reset flip-flop. Then we see how the set reset flip-flop is implemented using CMOS. Now it can be implemented using just NMOS transistor, or we can use a CMOS implementation. So both methods we use. Then there is a simpler method in addition to the one shown in 15.1.3. In the textbook, we are shown somewhat of a simpler method in 15.1.4. Lastly, we look at the D flip-flop. So basically, we are studying the circuit theory behind the latch, the SR flip-flop, and the D flip-flop. Now I know there's JK and other flip-flops that we have studied in other courses, but those, they are in this chapter 15, but for the moment I think if we know this information, we have developed a reasonably good understanding of, the basic cell in any memory system that actually holds the 0 and 1 information. Once you know this, once you have this knowledge, you can obviously build upon it and acquire more information depending on your interest and what you will do in this field, maybe when you start working as an engineer. All right, so let's start with the very first topic under 15.1, the latch. So what's a latch? A latch is a bistable circuit. Now remember, I told you that memory circuits consist of either the bistable static sequential type or the dynamic sequential type with capacitors. So right now we are talking about the first of these two, which is the static sequential circuit. And so, and a static bistable sequential circuit. And so a latch is one such example of a bistable static sequential memory circuit. Okay, so the basic definition of a latch is that it is a bistable circuit. That means it can have two stable forms or two stable states, either a 0 or a 1. So the latch is a bistable circuit that can stay indefinitely in an acquired state. So if it acquires a 0, it can just keep the 0 forever. If it acquired a 1, it can keep the 1 forever. That's what is meant by the word indefinitely. So I think this part you know already, but now we start understanding what are the electronic components, what is the circuitry consisting of, obviously CMOS devices and other devices such as power supplies and maybe clocks, etc., that are all essential to make the bistable work. So here goes. The rest of the slide gives you that information. So a latch consists of two cross-coupled logic inverters. So there's an inverter G1 and there's an inverter G2. And you'll hear this word or this phrase cross-coupled a lot. So what that means is you have one inverter, it has an input W, and then this symbol as an inverter, right? A triangle with a circle. The output of the inverter is the complement of whatever was at W. So if W is high, X is low. If W is low, X is high. Similarly, you have another inverter G2 that has Y as an input and Z as an output. This connection where the output Z goes back to the input of W, it gets connected. Similarly, the output of X is connected to the input of G2, the second inverter. That is the cross coupling. Cross coupling is where you connect two things, not both at the input side, but kind of at the output side. So not entirely on the output either, but the output of one goes to the input of the other and vice versa. So such a connection, you can also think of it as a feedback loop, right? Feedback path. The output of something comes back into the input. Such a connection we have seen in the past is called a feedback connection. So cross-coupling, feedback, these are all words, phrases that you're going to hear when we talk about latches. So that's the connection, right? So some more information here. So a latch consists of two cross-coupled logic inverters, G1 and G2. The two outputs X and Z are complementary. So what that means is when X is high, Z is low. Similarly, when X is low, Z is high. So they are opposite of each other. Now the latch has two stable operating points. So this is the latch. Here, to explain the operation of this latch, in our textbook, he uses this method. So he takes out one of these connections, just leaves the other in place, and then tries to guess and teach us how we can say that this circuit is a bistable circuit. So first thing to remember is that the latch has two stable operating points, and this is shown on the graph as A and C. Now what is this graph? It is some kind of transfer function, right? An input to output relationship. So when one of these inputs, for example VW, is low, in this closer to 0, the output is also close to 0. Similarly, when this input VW goes higher, we see that the output also has gone higher. So if you think of VW as the input and this VZ as the output, then they kind of work in synchronization. And there is a transition region in the middle, but the two stable points, meaning A is stable, C is stable, there's no changes happening, even if the input changes for a certain time and a certain time here. So two stable operating points shown on the graph as A and C. Stable point A, Vx is high, right? Vx, that is the output here, this Vx, is high at VOH, and Vz is low at the stable point A. Similarly, stable point C, Vx is low and Vz is high. So these are the two stable points. The stable state in which the latch stands at any given instant depends on the external excitation that forces it to that particular state. So at any given point, it can be either with Vx high, that means the output is VOH, which is the output high. Now this terminology, output low, output high, we get it from our study of CMOS inverters, right? OH meaning output high, generally that equals VDD or close to VDD. Similarly, output low is close to 0, you know that. So depending on whether it's a CMOS inverter or a MOS inverter, the quality of VOH and VOL, we have studied those. They can be either VDD or close to VDD, 0 or close to 0. But the two stable points will be when Vx is high and Vz is low, or Vx is low and Vz is high. Speaking of voltages, if you just want to talk logic, then you can say X is a 1, Z is a 0, or X is a 0, Z is a 1. So these two stable points, and we are using the graph to kind of understand the voltage movements, right? Sorry. So let's quickly look at the last sentence. The stable state in which the latch stands at any given instant. So at any given point, it's either in this stable point A or stable point C. It depends on the external excitation that forces it to that particular state. So something happened previously that push the latch either to point A or point C. The latch then memorizes this external action by staying indefinitely in the acquired state. So whatever it was that pushed it to one or the other, that's it. The latch is just sitting there, right? It won't make any changes on its own. Even though it may be connected to voltages and external circuits, no changes is going to happen. It'll be at A or at C. Those are the two stable points shown on the VTC, or the voltage transfer function. Okay. Now, with that understanding, in the textbook, we get a little more of a description on what exactly, how the bistable circuit operates in terms of its inverters' behaviors. So A and C are stable operating points in the sense that the circuit can remain at either indefinitely. Now there is a point B in the middle. B is an unstable operating point. The latch cannot operate at B for any significant period of time. So that means if the voltage, let's say the input, the VW, is pushing the circuit to stay at B, then that condition cannot remain true for a long time. The circuit either moves towards C or it moves towards A. Why? Because of the cross-coupling property. Okay, so a small disturbance at B, right? Let's say some small signal, very small, microvolts, hit the input, let's say this input VW, the voltage at W changes slightly, nanovolts change. So because of the slight disturbance and the amplifiers in the circuit, the disturbance starts getting bigger and bigger. It gets amplified. But because of the cross-coupling property, the inverters, the latch slowly moves in one direction or the other, and it keeps moving, but it stops when it arrives at point C. So even though a small disturbance, a small voltage at the input caused the circuits to start becoming an amplifier and keep amplifying, it won't happen indefinitely. It stops either at C. Similarly, if the small disturbance is negative, it pushes the latch down to a state where it stops at stable point A, which means you know what stable point A is, right? Vx is high and Vz is low. So either it will go to A or it will go to C, but it won't stay anywhere in the middle for too long. So this process, because of cross coupling, is also called a regenerative process, and this quickly shifts the operating point from B either upward to point C or from B downward to point A. Okay, so make sure you understand the inverter behavior, the amplifier behavior, and the cross coupling, so that stable points A and C are the only 2 points in which the inverter eventually, finally rests. There may be a small period of disturbance where things are moving around, but that is very small compared to, the other operation of the circuit. All right, so I introduced the latch to you. From here on, we'll use the basic idea behind the latch to look at flip-flops. So the first of the flip-flops is a SR flip-flop. So now that you have a latch, something happened and it's in state A or state C, one of the two stable states. We can't just say, okay, we've done our job, right? We need to be able to move the latch between the two states. And how do you make it move? You need a trigger mechanism. You need an external hit that causes the latch to move to where we want it to move. Either we want to force it to a 0 or we want to force it to a 1, right? And so the latch, along with the mechanism that can cause the change, the trigger mechanism, such a circuit is called a flip-flop. So the latch together with the triggering circuitry forms a flip-flop. So here we are shown a flip-flop, which is an SR flip-flop, set reset, where instead of just an inverter using an inverter gate, we have an OR gate. Well, actually we have a NOR gate, right? We have two NOR gates. So G1 and G2 are not just inverters anymore, they're actually NOR gates each. And what is the definition of a NOR gate? It requires at least two inputs, and the output is a OR complemented, right? So either R or Q bar goes through G1, and the output is a complement of R or Q bar. Similarly, this output is a complement of S or Q. And then I guess there's the cross coupling for the latch. Now, I know you know this pretty well, the truth table for an RS flip-flop. If both inputs are 0, then the output remains at whatever it was previously. Qn plus 1 means one cycle later. If set is 1, the output becomes 1. That means 1 is stored, the Q is 1 and 1 is stored. Similarly, if the reset is 1 and the set is 0, then the output, that means Q goes to 0, right? If both are 1, that is not allowed, it's an illegal condition. So I'm sure this you already know, but let's look at the circuits part of it. Again, in the circuit, two cross-coupled NOS gates form the basic latch. Each gate has a second output. So this gate has an R, this gate has an S. So each of these is called a trigger input. So these two trigger inputs together form the mechanism that can force the latch to change state. The outputs are labeled Q and Q bar. So along with two trigger mechanisms, we also have two outputs because it's a latch, two complementary, right? But the main output we are most focused on is Q, because Q bar just follows Q. It is the opposite. So raising S to 1 while leaving R at 0 gives the flip-flop is supposed to be set. No change if S then drops back to 0, right? We know that when S is set to 1, Q goes to 1. That means Q is 1. Set is when Q is 1. But if you take out S, nothing happens also. To change it back to the reset state or Q0, you have to force R to be 1, right? Okay. Both S and R are simultaneously raised to 1. That is a disallowed state. We don't allow it. Okay, with this mechanism, I think this basic logic you know already, so I don't want to spend too much time. Now we come to the circuits part of it. Now 15.1.3. So previously here we saw, in the previous slide, we saw how to implement this using a NOR gates, right? But a NOR gate consists of a lot of inverters, could consist of inverters, not always necessary. But in this topic called CMOS implementation of SR flip-flops, here in our textbook, we are shown a definite CMOS implementation. But instead of just taking a basic flip-flop, what they have done is they've added a clock also. So it's slightly more complicated than a simple SR. This is now a clocked flip-flop, a clocked SR flip-flop. So now I think you're more familiar and comfortable with circuits like this. So what do we see here? There are two inverters, right? Q1, Q2 forms one CMOS inverter. Q3, Q4 forms another CMOS inverter. So we have G1, G2. Now this circuit is not in our textbook. I had to create it myself. So maybe this is helpful to you. But this G1 you can think of as Q3, Q4. So this 2 is G1. Similarly, G2 consists of Q1, Q2. Then you have two more sets of transistors which form the AND gates, right? So here we're using an AND version. Previously we saw a NOR version. Here we'll use AND gates and then inverters, so basically NAND gates, to help us implement this clocked version of an SR flip-flop. Okay, so two cross-coupled CMOS inverters form the latch. So this and this are the basic latch. Set reset signals are each in AND connections with the clock inputs. So we have a set input and a clock input. Both are going through, are attached to NMOS devices which act as a AND circuit, right? So anything in series like this, you probably know by now, is an AND circuit. And the output of this AND circuit, which is, the S shown here, then is fed to the inverter. Similarly, the output of reset and phi, this output, is fed to the other inverter, G2, which consists of Q1, Q2. Now the feedback is also there, the cross coupling. So the output of G2 is connected to the input of G1. Similarly, the output of G1 is connected to the input of G2. So that cross coupling is also here. So that makes it a slightly complicated circuit, but I'm sure by now you're able to handle this. So the flip-flop can be set or reset only when the clock phi is high. So now for the flip-flop, the latch to change state, you have the S and the R like in the previous case, but the S and the R also operate only when the clock is going high. So we added one more condition to the operation of the flip-flop. Using S and R you change, but S and R, either S or R, only works when the clock input is also a high. The clock pulse is a high. So when the clock pulse is a low, it doesn't matter what you do with S and R and all that, no changes happen. The bistable still stays in its locked state. Okay? All right. So a little more on how this works. So let's say that the flip-flop is in its reset state. That means Q is 0 and Q1 is 1. So that means if you look at the logic diagram, the reset state means Q is 0. Of course, Q bar then is 1, right? So let's begin by assuming that's where the flip-flop is at the moment. Now start with a high VDD signal applied to the S input while R is held low, right? Obviously S and R have to be opposite. We are not allowing them to be both high. That's illegal. Now when the clock phi goes high, the two NMOS devices, Q5 and Q6, will conduct, right? Because we've already put a high on S, now a high is coming in on clock. So this branch, Q5, Q6, which is an AND really, because there are two NMOSs in series, this acts like a pull-down network, right? You know what that is. NMOS devices love when you give high inputs on them because they start to conduct. And here what happens is, because on this side, on the source side, you've connected them to ground, this acts like a pull down network, and this output point here, which is Q bar, gets pulled to ground. So the high applied to S and phi is pulled down to ground, right? That's the definition of a pull down network. So what happens then is Q bar, this point, which is the output of this AND gate, goes to 0, right? So when the clock phi goes high, both NMOS Q5 and Q6 will conduct in an AND condition, pulling the voltage VQ bar down to ground. If VQ bar goes below the threshold of Q3 and Q4, now this Q bar is also connected as the input of the inverter Q4, Q3, right? So if Q4 now goes below the threshold, right? Remember Q3 and Q4, they have a VM. We studied this previously. It's when the inverter switches, right? When the input voltage to the inverter, remember the inverter is sitting in a reset state, right? Reset meaning Q is low. So when you lower the input voltage below VM, the threshold, then Q3, Q4 will flip. That means the output will go high because it is currently at a low state, right? It's at a reset state. So if VQ bar goes below the threshold VM of the Q3, Q4 inverter, this inverter will switch states, or at least begin to switch states, and its output VQ will rise. So Q will reach a 1, which is a high. So you see how applying just a clock at the time when S is high causes the inverter to flip. And we know that when this flips to Q, the opposite, the latch forces the other to switch to Q bar. So this increase in VQ here slightly, right? It's not fully, but it's just starting to go a high. This increase in VQ is fed back to the input of the Q1, Q2, causing its output VQ bar to go down even further, right? Because of the cross coupling, this goes in as the input to this inverter, and that inverter now goes even further lower. That means Q bar goes low, and that pushes the output of Q even higher, so because they are cross coupled. So basically what happens is this dynamic process, regeneration process, eventually leads to the latch going to one of its two stable states. And what is a stable state? It was previously at reset, now it goes to set, which means the Q will be at 1 and Q0 will be at 0. So essentially we have pushed the latch from being in reset to being in set. And set means Q is high, Q bar is low. Q means this inverter Q3, Q4, G1 is high, it went high, and the other inverter went low. Okay, so I hope this circuit consisting of two inverters and two NMOS devices in series forming an AND circuit helped you see how the set function worked. Now the same thing can be shown for the reset, which unfortunately I haven't written here, but the same logic holds, right? So using when S goes 0, R goes high, N clock goes high, then we can see that this Q bar output can be shown to go high and Q will correspondingly go low. Okay, so that is basically the circuit operation of the SR flip-flop. This portion in blue only talks about the AND portion of it, this portion, but this AND in conjunction or together with the inverters, the G1, G2, make sure you understand how all this comes together. So a couple more important things to remember. Even though we described how the flip-flop is working, two important assumptions are in here. One, transistors Q5 and Q6, they have to have sufficient current capability to actually push Q down, right? So for that to happen, the transistors need to have a certain area, certain silicon, and VDD has to be sufficiently high. So all that circuit stuff has to be available for this to work. That's condition one. Second condition also is that both S and phi, the set signal, for example, S signal, has to be long enough, right? You can't just say, I'm going to give it a shot at S and then disappear. No, the set signal, similarly, the clock also has to have a certain width, certain duration, and that only will ensure that this flipping business happens, the change from one state to another. So one has to do with the duration of the pulse and the S signal, S input, and the other has to do with the silicon area, the W by L, the VDD, and all that stuff for the individual transistors, both for the AND function and for the inverters. So obviously in our course today, we will spend a lot of time doing problems related to these two conditions. We find minimum W by L ratios that have to be satisfied. We find the width of the duration of the pulse, TPH, TPL issues. So those problems you'll see in my next recording. 15.1.4, one more important thing. It just says that the R and phi AND gate, similarly the S and phi AND gate, those you can employ using PTL, pass transistor logic. This is the condition you see here shown in the drawing, instead of just using regular AND gates. So you can use pass transistor logic, and more importantly, he tells us that this pass transistor logic approach is what is used for SRAM chips, static RAM chips. Now, we don't study too much of this, but make sure you know why he's pointing out the importance of PTL in implementing SR, clocked SR flip-flops. Okay, problems, we will come back. The other important topic, the theory, is the D flip-flop circuit. I told you that we're going to study that too. I'm sure you know the logic of the D flip-flop. You've seen this in other courses. But a D flip-flop is an edge-triggered flip-flop. So what that means is you can have any signal at D, either plus, it's only a one input flip-flop, right? Only D exists. But the clock exists too. And whatever is on D changes on the rising edge of the clock. Now you can also have falling edge, but let's stick with rising edge. So when the clock pulse is going high, then whatever is on D comes to the output. So whatever is on D goes to this Q. Similarly, on the rising edge of the clock, if you had a 0, you get a 0 as the output. If you had a 1 and the rising edge of the clock sees that, then you get that 1 on the output. So as the clock goes high, the flip-flop acquires the logic level that existed on the D line just before the rising edge of the clock. Such a flip-flop is said to be edge triggered. Okay? All right. So here is an implementation, a circuit implementation of the D flip-flop. You still have the same latch. It's just shown in a different form, but you have cross coupling, you have the feedback path through another transistor to another PTL gate, actually, pass transistor logic gate. Here's another pass transistor logic gate. And you have the clock pulses. So when the clock is low, the flip-flop is in the memory or rest state. Signal changes on the D input line have no effect on the state of the flip-flop when the clock is low. The feedback loop is closed through here when the clock is low. When the clock is high, input D is connected to the flip-flop through a switch. As the clock goes high, the flip-flop acquires the logic level that existed on the D line just before the rising edge of the clock. Such a flip-flop is said to be edge triggered. Okay, so whatever was on D, as the phi goes high, that gets transferred. Okay, so that is the basic property. And how do you implement in circuits? Again, all you need are two inverters, CMOS, and you need two AND gates, one here and one here. And this is implemented through pass transistor logic, maybe with just one NMOS or maybe with a CMOS transmission gate, we don't know. But this is the basic circuit. Now, one of the disadvantages is that if D changes while the clock is high, those changes go through. But if you want to ensure that such changes don't go through and only what existed at D at the instant the clock flips, then you need what is called a master-slave D flip-flop, which requires two of these. It's shown in the chapter, but I'm not going to address that too much. So for our purposes, we just need to know that with one latch consisting of two inverters and these pass-through logic, we can implement a D flip-flop. Okay, that's it. Sorry, I'm taking slightly more time, but with that, we come to the end of the theory of this section 15 from this chapter 15. Okay, next recording, problems.